Astronomers in Hawaii have released what's being called the most structurally revealing imagery of interstellar comet 3 Atlas. These images, captured by amateur observer COPA stars from the dark skies of Hanikaha, Hawaii, have provided a definitive view of a rare and controversial optical phenomenon, a razor-thin anti-tail projecting toward the sun. These stacked exposures, processed using advanced AI refinement techniques, confirm the presence of a highly cumulated stream of material that is currently challenging standard cometary models. This is happening right now. The observation, recorded using a C-STAR SSS-50 SMART telescope, leverages the unique vantage point of Earth's current position relative to the comet's orbital plane. According to data released this week, the imagery reveals a nucleus structure that appears distinct from the diffuse comas typically associated with solar system comets. Instead of a chaotic cloud of sublimating ice and gas, the Colopa star's data shows a concentrated, coherent projection that has ignited this fierce debate within the astrophysical community regarding the object's composition and origin. Scientists are analyzing this data immediately. So the primary focus of this new data set is the anti-tail. And look, this is a feature that usually represents a geometric illusion caused by heavy dust particles lagging behind a comet's orbit. However, the precision of the structure visible in the Hawaii images is unprecedented. Mainstream astronomers are currently interpreting this as a result of Earth passing through the comet's orbital plane, viewing the dust sheet edge-on. Conversely, dissenting voices, including researchers tracking the object via platforms like Space Tracker, are suggesting the structural integrity of the tail implies a density and mass inconsistent with loose dust. The implications are significant here. Current analysis suggests that for a dust tail to appear this sharp and linear, the particles must be significantly heavier than typical cometary grains. This has led to immediate speculation about the presence of heavy metals or dense rocky materials within the nucleus. As of the 30th of November 2025, teams at major observatories are cross-referencing the Hanukkah data with spectroscopic readings to determine if the dust is actually composed of standard silicates or something more anomalous. We're witnessing this in real time. Now, these findings from Hawaii aren't isolated. They corroborate a growing body of evidence collected throughout November 2025 that indicates 3 Atlas is behaving in ways that defy easy categorization. The clarity of the Colopa star's imagery has moved the discussion from theoretical modeling to direct observational analysis. The question is no longer whether the anomaly exists, but what physical mechanism is capable of maintaining such a precise structure against the chaotic forces of the solar wind. Let that sink in. Astronomers are now prioritizing the analysis of this anti-tail geometry as the object approaches its perihelion. The distinction between a natural projection effect and a physical structural anomaly has become the defining scientific question of this launch window. With closest approach scheduled for the 19th of December 2025, the window for gathering definitive data is closing, making high-resolution captures like those from Hanukkah critical to the ongoing investigation. This changes everything, man. Current reports indicate that the Colopa star's imagery was acquired through a process of stacking multiple short exposures to eliminate atmospheric turbulence, a technique that has allowed for subarc-second resolution of the comet's inner coma. The resulting image displays a level of contrast that highlights the sharp boundary between the comet's main tail and the anomalous anti-tail. This specific observational technique has proven essential in cutting through the glare that has obscured details in previous observations. Researchers are focusing on this contrast. According to the latest technical breakdown from the observation team, the anti-tail remains visible for an extended duration, which is unusual for transient geometric alignments. Typically, as Earth moves through the orbital plane, such features appear and vanish within a predictable time frame. The persistence of the 3I Atlas ante tail as documented in the Hawaii footage suggests a continuous ejection of material or stable physical structure that remains aligned with the solar vector. And look, this is not speculation. The data from the CS50 observations is now being integrated into the global tracking database managed by agencies monitoring the object. Space Tracker has updated its orbital parameters based on these new luminosity profiles, refining the estimated size of the nucleus and the density of the surrounding coma. The consistency of the anti-tail feature across multiple observing sessions in Hawaii provides a robust baseline for comparison with incoming data from space-based assets. Scientists are paying attention to this. The significance of the Hanukkah observations lies in their ability to resolve the neck of the comet, the point where the coma transitions into the tail structures. In typical comets, this region is turbulent and diffuse. The Kolapa star's images, however, show a region of surprising order and linearity. This observation connects directly to the core mystery of why 3A Atlas appears to maintain a coherent shape despite the intense solar radiation pressure it's currently experiencing. This leads to a critical question. If the object is a standard dirty snowball comet, the outgassing should differ in intensity and direction, creating a more ragged appearance. The smoothness and sharpness of the features seen in the Hawaii images argue for a nucleus that is either monolithic, a single solid rock or metal body, or one that is outgassing in a remarkably uniform manner. Researchers are currently running computer simulations to see if any combination of ice and dust ratios can reproduce the exact visual signature captured in these images. The latest analysis shows a discrepancy. When standard commentary models are applied to the 3 Atlas data, they predict a broader, more fan-like distribution of dust for a comet at this distance from the sun. The razor-thin quality of the anti-tail observed by Kolapa stars deviates from these predictions by a statistically significant margin. This deviation is what's driving the current urgency in the scientific community to obtain follow-up spectroscopy. Think about that for a second. To understand the gravity of this observation, we need to look at the mechanics of cometary tails. A comet typically has two tails. An ion tail of charged gas blown directly away from the sun by solar wind, and a dust tail that curves along the comet's orbit. The anti-aisle is an optical illusion that occurs when Earth crosses the comet's orbital plane, causing the curved dust tail to appear to point toward the sun. For this feature to appear as a sharp line, the dust particles must be large and heavy, resisting the push of sunlight. Here's the critical point. The specific columnation or parallel alignment of the material seen in the Hawaii images implies that the particles are not just heavy, but also remarkably consistent in size and mass. If the particles varied widely in size, solar radiation pressure would sort them into a fan shape, blurring the line. The fact that the line remains sharp suggests a uniform material release. This uniformity is rare in natural comets, which typically release a chaotic mix of fine dust, pebbles, and gas. This connects to the controversy. This uniformity is the specific data point that skeptics of the natural comet hypothesis are seizing upon. Avi Loeb and researchers aligned with the extraterrestrial hypothesis are arguing that this level of structural order hints at engineered stability. They're proposing that what we're seeing is not a dust trail, but a stable structural component or a controlled emission designed to maintain orientation. While this remains a minority view, the data from Hawaii doesn't immediately rule it out, as standard dust models struggle to explain the extreme columnation. Scientists are actively debating this. Mainstream astronomers, however, maintain that the heavy dust explanation is sufficient, provided the comet originated in a stellar environment that favored the formation of dense metal-rich grains. They're arguing that 3 Atlas may be a fragment of a differentiated planetary body a metal core exposed by a collision rather than a primordial ice ball. If verified, this would explain the heavy particles necessary to create the sharp anti-tail without invoking artificial origins. This development is crucial. As of the 30th of November 2025, NASA and affiliated research institutions are using the Colopa stars data to calibrate the exposure times for the upcoming James Webb Space Telescope observations. The ground-based data from Hawaii serves as a pathfinder, indicating exactly where the instrument should look to capture the spectrum of the anti-tail material. The goal is to detect the chemical signature of the particles. Silicates would point to a natural rocky origin, while refined alloys would be the smoking gun for artificiality. We're witnessing the scientific process here. The collaboration between amateur astronomers like Colopa stars and professional institutions is a defining feature of this event. Because 3 Atlas is an interstellar object, its trajectory and brightness are unpredictable. The continuous monitoring provided by the global network of C-STAR's S50 users ensures that no sudden brightening events or structural changes go unrecorded. The Onoka dataset is currently considered the benchmark for ground-based optical imaging of this object. Let that sink in. The location of the observation is also relevant. The atmospheric stability above Honuka, Hawaii, combined with the dark sky conditions, allowed for a signal-to-noise ratio that's difficult to achieve in mainland observatories. This clarity is what enabled the AI processing algorithms to refine the image without introducing artifacts. The validity of the razor-thin description depends entirely on the fidelity of this data, which has now passed initial peer review within the amateur astronomy community. This is happening now. As we speak, Space Tracker is aggregating this imagery with orbital data to refine the trajectory models. There's a slight non-gravitational acceleration acting on 3 Atlas, a push that's typical for comets releasing gas. However, the direction of this push relative to the anti-tail orientation is currently under scrutiny. If the antitail is a stream of heavy particles, it shouldn't be generating significant thrust. If the object is accelerating, the thrust must be coming from a different mechanism, one not immediately visible in the optical spectrum. The significance here is high. The disconnect between the visible structure and then the measured acceleration is the core mystery driving the current news cycle. Standard physics dictates that the material we see leaving the comet, the tail, is the same material providing the thrust via Newton's third law. But if the tail is composed of heavy, slow-moving dust, it creates very little thrust. For the object to accelerate as observed, there must be a high-velocity gas jet that's somehow invisible or obscured in the current images. Researchers are looking for this jet. The Hawaii images don't show a bright, distinct jet separate from the anti-tail. This absence complicates the picture. It forces astronomers to hypothesize that the gas jets are perhaps symmetric or diffuse enough to be washed out by the glare of the nucleus. Alternatively, the heavy dust theory might be incomplete. The possibility that the anti-tail itself is related to the propulsion or non-gravitational movement can't be entirely dismissed until the December 19 close approach provides better angles. This raises a major question. Could the 3 Atlas nucleus be rotating in a way that focuses the dust release? The columnation seen in the Hawaii images could be the result of a specific rotation pole orientation. If the comet's pole points directly at Earth, the material released from the equator would form a disk that we see edge on. This wheel on-edge appearance would mimic a razor-thin anti-tail. Determining the rotation period and pole orientation is the next immediate priority for observers. Scientists are working to determine this. Light curve analysis from the last 72 hours shows a steady brightness which argues against a rapid chaotic tumble. A stable rotation supports the disk hypothesis. However, For a comet to maintain such a stable rotation while outgassing vigorously usually requires a large massive nucleus to act as a flywheel. Estimates of 3 Atlas's size are still refining, but it appears small under a kilometer. A small active comet usually tumbles chaotically. The stability is another anomaly. That's the critical point here. The stability of the structure seen by call-up stars suggests an internal density distribution that stabilizes the rotation. This brings us back to the meteorite hypothesis. A dense iron-nickel core would provide the angular momentum inertia needed to keep the spin stable and the dust release planar. This fits the visual data, but requires the object to be a shard of a destroyed planet core, a relatively rare class of object known as an M-type asteroid. Yet, it's behaving like a comet. This is unprecedented. The term interstellar is key here. 3 Atlas is not from our solar system. Its composition reflects the star system of its birth. The fact that it looks so different from our local comet, specifically in this anti-tail structure, is direct evidence of different formation conditions. The heavy dust might be common in the system it came from. We're effectively sampling the geology of an exoplanet system using a telescope in Hawaii. Here's why that matters. If 3 Atlas is a metallic shard acting like a comet, it challenges our understanding of planetary destruction. It implies a violent history in its home system. But if the engineered stability argument from Loskamp holds any water, the implications shift from geological to sociological. While the data currently leans 99% toward natural explanations, the 1% uncertainty is driven entirely by the stubborn structural anomalies that refuse to fit neatly into existing models. Scientists are debating this actively. The natural dust sorting theory is the current front runner. Solar radiation pressure pushes smaller particles away faster. Large particles lag behind. This sorting mechanism can create sharp lines under the right viewing angles. The Hawaii images show a line so sharp, however, that the sorting must be incredibly efficient or the particle size distribution must be exceedingly narrow. Nature rarely creates monodisperse. That's single-size particle clouds. Usually, it's a messy mix. This is the core conflict. The monosperse appearance is what looks artificial to the trained eye of skeptics. Industrial processes create uniform particles. Nature creates distributions. The uniformity implied by the sharpness of the anti-tail in the Colopa star's images is the specific data point fueling the technosignature discussion. While likely a natural coincidence of viewing geometry, it's statistically unlikely enough to warrant the intense scrutiny it's receiving. This changes the narrative. Now, reporting on this event requires acknowledging that anti-tails are a known phenomenon. Comets Arne Roland in 1957 and Pan-STARRS in 2013 exhibited prominent anti-tails. However, in those cases, the feature was clearly a broad fan of dust-seen edging. The 3 Atlas feature is distinct in its narrowness. Comparisons to historical comets show that while the type of feature is known, the quality and geometry of this specific instance are outliers. Researchers report this distinction. The C-Star S50, the instrument used for this discovery, represents a democratization of this data. In the past, only large institutional telescopes could resolve these details. Now, a network of observers can track the evolution of the tail hour by hour. This high cadence of data is crucial because if the tail flickers, pulses, or changes angle independently of Earth's motion, the static dust theory collapses. Current observations reveal stability. So far, the feature appears stable. This stability supports the orbital plane crossing explanation. If the tail were a propulsive jet, we might expect variability. The fact that it remains a steady razor-thin line as Earth moves suggests we're indeed looking at a static sheet of material. This reinforces the heavy dust conclusion, but leaves the monodisperse mystery unsolved. Why is the dust so uniform? Scientists are engaging with this. NASA's response has been to continue its planned observation schedule without deviation, signaling confidence in the natural explanation. However, the agency has acknowledged the public interest and the unique visual properties of the comet. The space tracker community has become the de facto hub for these real-time updates, bridging the gap between the raw data from amateurs and the peer-reviewed conclusions of professionals. The implications are significant. As we move into December 2025, the viewing angle will change. Earth will move out of the orbital plane. If the antitail is a projection effect, it should widen and fade. If it remains a tight columnated beam, even after we leave the orbital plane, then the projection effect theory is falsified. That would be the moment the scientific consensus fractures. The Hanukkah images provide the baseline against which this future widening will be measured. We're witnessing this in real time. The specific date of the Hanukkah capture, late November 2025, places it exactly in the critical window before the plane crossing completes. The next 2 weeks are the test. Every night that the anti-tail remains razor thin adds tension to the model. If it persists past the geometric alignment window, researchers will be forced to consider non-gravitational confinement mechanisms, magnetic fields, or in the most extreme speculation, artificial containment. This leads to the next step. Spectroscopic analysis is the only way to solve the particle composition question. Light reflected off the dust carries the fingerprint of the materials. If the antitail is iron-rich, the spectrum will show specific absorption lines. If it's water ice, it'll look different. The brightness of the feature in the Hawaii images suggests a high albedo, that's reflectivity, which is consistent with ice. But the mechanics require heavy mass, which suggests metal. This ice versus metal paradox is the current focus of laboratory modeling. Scientists are analyzing this paradox. One proposed solution is dusty ice with a high metal content pebbles of iron encased in ice. As the ice sublimates, the heavy pebbles are left behind in the orbital plane. This hybrid model satisfies both the reflectivity data and the mass requirements. It describes a comet formed in a region of a protoplanetary disk where metals and ices coexisted, a snowline boundary in an alien solar system. Think about that for a second. The concept that we're visually inspecting the snowline geology of a distant star system using a telescope bought by an amateur astronomer is a testament to the current state of observational science. The 3i Atlas event is dissolving the barrier between big science and public participation. The data point is valid. The mystery is real, and the resolution is pending. Here's what's critical. The controversy angle provided by Avi Loeb serves a function in this scientific process. It forces a rigorous defense of the null hypothesis. Because the claim of engineered stability is on the table, mainstream scientists must calculate the dust dynamics with higher precision than usual to prove it isn't artificial. The result is a better understanding of cometary physics. Regardless of the final conclusion, the razor-thin anti-tail of 3 Atlas is stress-testing our models of solar-wind interaction. This connects to the core mystery. Why does the columnation suggest a meteoric nucleus? A low-density icy nucleus would release gas in all directions, entraining dust in a diffused cloud. A high-density metallic nucleus would have higher thermal conductivity, heating up more uniformly or perhaps only on active spots, potentially creating distinct jets. But a meteoric object usually doesn't outgas at all. 3 Atlas is doing both, acting like a rock and a comet simultaneously. The latest data supports this hybrid nature. The C-star S50 images show a compact central condensation, the bright spot in the middle that's smaller than expected for the amount of tail visible. This implies a small hyperactive nucleus, a small engine making a big cloud. This efficiency is another data point that fits the artificial narrative. Small probe, big sail, but also fits the differentiated core narrative. which is a small metal body with surface volatiles. The data doesn't yet distinguish between the two. Scientists are actively monitoring this. The role of AI processing in the Colopa star's images can't be overlooked. The refinement mentioned in the report involves deconvolution algorithms that sharpen the image based on known point spread functions. Critics argue this can introduce artifacts creating lines where there are none. However, the raw data has been made available, and independent processing confirms the linear structure is present in the signal, not just the processing. This is a validated finding. As of today, the existence of the linear anti-tail is a confirmed fact. The interpretation is the variable. The space tracker community is currently aggregating similar images from observers in the southern hemisphere to build a 3D model of the tail. This stereoscopic approach, using the rotation of the Earth to get slightly different angles, will help define the true thickness of the dust sheet. Researchers are waiting for these results. If the sheet is truly as thin as it looks, thick across millions of kilometers of length, it represents a dynamic stability that's hard to simulate. Solar wind is turbulent. Interplanetary magnetic fields are turbulent. For a sheet of dust to remain razor thin over astronomical distances is like blowing smoke in a hurricane and having it form a straight line. This dynamic impossibility is what keeps the mystery label firmly attached to 3I Atlas. This is unprecedented behavior. Current theories involve shepherding forces. Could the comet have a magnetic field? If the dust is charged, which it becomes in sunlight, and the comet has a magnetic field, the field lines could confine the dust. But comets aren't known to generate their own magnetic fields. Planetary cores, however, do generate magnetic fields. If 3 Atlas is a magnetic planetary core, it could theoretically organize its own tail. Let that sink in. A magnetic interstellar traveler. This hypothesis would bridge the gap between the natural and structured camps. It's natural. It's a core but has structure through magnetic confinement. This would explain the columnation without aliens, but it would be a first in history discovery for cometary science. The Hawaii images are the first visual hint that this magnetic confinement might be operating. Scientists are investigating this possibility. Magnetometers on passing spacecraft would be needed to confirm this, but 3 Atlas is too far for direct magnetic measurement by near-Earth satellites. We have to infer it from the motion of the charged dust. The razor-thin anti-tail is exactly what a magnetically confined dust plasma might look like. This moves the debate from dust physics to plasma physics, adding another layer of complexity to the analysis. This connects to the full context. The C-Star S50 used by Colopa stars is a small aperture telescope. The fact that it picked this up speaks to the brightness of the feature. A dim diffuse tail would require a large mirror. A bright sharp feature is visible to small optics. This brightness per square arcsec surface brightness indicates a very high density of material. There's a lot of stuff in that tail. Researchers report high density. High density means high mass loss. 3 Atlas is bleeding material into space at a prodigious rate. If it's small under 500 meters, it can't sustain this rate for long. It should vanish. The fact that it persists suggests either it's much larger than it looks and dark, or the material is extremely reflective. So we overestimate the amount, or the release mechanism is highly efficient. This raises a timeline issue. With perihelion approaching in December 2025, the heating will increase. If the mass loss accelerates, the anti-tail could thicken or disrupt, or if it's magnetically confined, it might hold its shape even as the solar wind pressure quadruples. The next 3 weeks of observation from Hawaii and elsewhere are the crucible for these theories. As of the 30th of November 2025, the status is clear. We have a verified high-quality image of a physically impossible-looking structure attached to an interstellar object. We have a confirmed closest approach date of December 19. We have a scientific community divided between extreme natural physics and open-minded anomaly hunting. And we have a global network of trackers watching every pixel. This is the definition of breaking science. The immediate next steps involve the transition from optical imaging to spectral imaging. The visual data from Hawaii has set the stage. Now the chemical data must follow. Observers are currently attempting to lock onto the anti-tail specifically with spectrographs to isolate its composition from the main coma. Scientists are actively scheduling this. Upcoming observations in early December will focus on the infrared bands where thermal emission from the dust can reveal the particle size directly. If the infrared data matches the visual razor-thin data, the heavy dust model will likely be confirmed. If there's a mismatch, the mystery deepens. Current observations reveal a waiting game. As of today, the 30th of November 2025, the 3 Atlas anti-tail remains the most compelling astronomical object in the sky. It's a daily reminder that our models of the universe are based on local examples, and the galaxy is capable of sending us things that break those molds. Whether natural anomaly or something more, the image from Hanukkah is now the reference point for all future discussions. This is happening now. The scientific method is grinding forward in real time, fueled by data from amateur backyards and professional observatories alike. We're watching the process of discovery unfold pixel by pixel, frame by frame. The final answer may not arrive until the object is outbound, but the data collected right now, this week, will be the key to unlocking it. The implications are significant. Keep your eyes on the reports from the Space Tracker Network in the coming days. As the angle shifts, the truth about the razor-thin tail will be revealed by geometry itself. Until then, 3 Atlas remains a sharp, bright line drawn across our understanding of the cosmos. That's the situation as of